So if we want to derive the formula for the cross product, the first thing that we should start off with is working out the area of the parallelogram defined by the vectors a and b. So here we have the vector a, and here we have the vector b, and here in white this is the parallelogram defined by the vectors a and b, and we want to know what is the area of that. Now, when you want to work out the area of a parallelogram, the way that you can do it is you can imagine dropping a straight line down from here, which will have length equal to the length of the component of b that is perpendicular to the vector a, and then you can imagine chopping off this red triangle here and bringing it over here to make a rectangle, and indeed the area of the parallelogram then is going to be the same as the area of this rectangle here. And to work out the area of that rectangle, we just need to know the area of this the length of this side times the length of this side. So the length of this side of the rectangle is very easy because, of course, it's the same as this side of the parallelogram, which is just the modulus of the vector a. Then we just need to know the length of this side of the rectangle. Now that's the length of the component of vector b that is perpendicular to the vector a. So if we call the angle between the two vectors theta, then the length of this side of the rectangle is going to be the modulus of the vector b, which is the length of this hypotenuse of this right angled triangle here, times sine of theta. So in fact, the length of this rectangle is just going to be equal to the modulus of a times the modulus of b sine theta. So this is going to be the area of that parallelogram defined by a and b. We're going to use the dot product to try and work this out. So prior to this video on the cross product, in the playlist on calculus, there is a video on why does the dot product work. So I'm going to assume that you have watched that video and you understand the dot product. So a dot b is equal to the modulus of a times the modulus of b times cos of theta, and this is why we're going to be able to use the dot product, because from the cos of theta, we can work out what sine of theta is going to be equal to using some trigonometric identities, and we have a formula in terms of components for what the dot product is equal to. So if we say that vector a is equal to a1i plus a2j plus a3k, as before, and vector b is equal to b1i plus b2j plus b3k, then the formula in terms of components for the dot product is a1b1 plus a2b2 plus a3b3. So cos of theta is equal to a1b1 plus a2b2 plus a3b3 divided by the modulus of a times the modulus of b. Now we could easily work out what the modulus of a and the modulus of b are in terms of these components. However, we don't actually need to do that. It will just make the formula more ugly, and indeed it will just cancel later on, as we'll see. So we're just going to leave it as the modulus of a times the modulus of b. So we're now going to use the fact that this trigonometric identity is true, that for any angle theta, sine squared theta plus cos squared theta is equal to 1. Now we know what cos of theta is going to be equal to, so we can now rewrite this as sine squared of theta is equal to 1 minus cos squared of theta, and we can then substitute this in for what the value of cos of theta is equal to. So that says that sine squared of theta is going to equal 1 minus a1b1 plus a2b2 plus a3b3 all squared over the modulus of a squared, the modulus of b squared. So we've just taken all of that, squared it to get what cos squared theta is equal to, and we've got 1 minus all of that. And now what we're going to do is take the square root of this to find out what sine of theta is equal to. So taking the square root, we get that sine theta is equal to the square root of, and now what I've done is I've got it all under one denominator, so I've multiplied 1 by the modulus of a squared, the modulus of b squared, so that we can write it as the modulus of a squared times the modulus of b squared minus all of this thing, a1b1 plus a2b2 plus a3b3, all of that squared, and then the whole thing is now over the modulus of a squared times the modulus of b squared, and then we need to take the square root of that entire thing. Now you might wonder, why is there not a plus or minus here? Now it is true that either the positive version of this or the negative version of this will satisfy this formula here. However, think about the scenario that we're actually dealing with, theta is this angle between the vector A and the vector B, and it is always going to be between 0 and 180, because we're always interested in the smallest angle between A and B. So we wouldn't be interested, for instance, in the angle all the way round like this. We're interested in that smallest angle between A and B, and that's always going to be between 0 and 180. And if you consider the graph of y is equal to sine of x, which I've just drawn here, remember the graph of sine of x is always positive when the angle is between 0 and 180, and then it becomes negative between 180 and 360. So actually we're not interested in the negative answer of this, because for our scenario, sine of theta is always going to be a positive number. Another argument for that is, remember, we're trying to find this area. The modulus of A is going to be a positive number. The modulus of B is going to be a positive number. So sine of theta also needs to be a positive number. If you put in a negative number there, then you're going to get a negative answer for what the area is equal to. So again, that's another argument for why we're only interested in the positive square root. We're not interested in the negative square root. But yes, of course, the negative square root would satisfy this formula.